Hey everyone, tonight we're going to dive into something that keeps a small community of scientists awake at night, listening to the cosmic static that fills the space between stars. It's the search for extraterrestrial intelligence, or SETI, and specifically those moments when the universe seems to whisper something back, signals that don't quite fit the patterns we expect from natural phenomena but don't quite announce themselves as messages from another world either. There's something profoundly lonely and hopeful about the whole enterprise. Picture massive radio telescopes turning slowly across the night sky, their dish antennas pointed toward distant star systems, collecting electromagnetic whispers that have traveled for years or decades or centuries to reach us. Most of what they hear is exactly what you'd expect. The background hum of hydrogen gas between galaxies, the predictable pulses of spinning neutron stars, the radio signatures of cosmic events we've learned to recognize and catalog. But every so often something else comes through. A signal that's a little too structured to be natural, a little too brief to be definitively artificial. A cosmic murmur that makes the researchers pause and wonder if they've just overheard a conversation between civilizations separated by distances that dwarf human imagination. The famous ones have names that have entered popular culture. The WOW signal detected at Ohio State University in 1977, strong enough and unusual enough that the astronomer monitoring the printout scribbled "WOW" in the margin. It lasted 72 seconds, came from the direction of the constellation Sagittarius, and has never repeated despite decades of follow-up observations. Was it a message? A natural phenomenon we don't understand? Equipment malfunction? We still don't know. But the WOW signal is just the most famous example of a much larger phenomenon. SETI researchers have detected hundreds of candidate signals over the past 50 years. Brief radio bursts, structured patterns in cosmic noise, electromagnetic signatures that don't match anything in our catalogues of known astronomical objects. Most turn out to have mundane explanations when examined more closely. Some remain unexplained but fall below the threshold of statistical significance that would justify claiming a detection. And a few, just a few, sit in that uncomfortable middle ground where they're too interesting to dismiss but too ambiguous to celebrate. They're the cosmic equivalent of hearing footsteps in an empty house, glimpsing movement in your peripheral vision, feeling like someone's watching you from across a crowded room. They make you pause, make you wonder, make you question what you think you know about our place in the universe. Tonight, we're going to explore these ambiguous signals, these cosmic murmurs that suggest we might not be alone but stop short of proving it. We'll think about what it means to listen for intelligence in the static of deep space, what kinds of messages we might expect to receive, and what it says about humanity that we've spent decades pointing our most sensitive instruments toward the stars, hoping to hear an echo of our own curious nature reflected back from the cosmic dark. Because whether or not we ever detect a definitive signal from another civilization, the search itself reveals something profound about who we are as a species and what we hope to find when we look beyond the boundaries of our small blue world. To understand what makes these cosmic murmurs so compelling, we need to step back and consider humanity's long relationship with the idea of other worlds and other minds. The notion that we might not be alone in the universe isn't a modern invention born from science fiction and radio telescopes. It's an ancient question that has haunted human imagination for millennia. The Greek philosopher Democritus, writing in the 4th century BC, proposed that infinite worlds must exist beyond our own, populated by beings we could scarcely imagine. His contemporary Epicurus went further, arguing that it would be absurd to think that in an infinite universe, Earth would be the only world to develop life. These weren't just philosophical speculations. They were attempts to grapple with the fundamental question of cosmic loneliness that still drives SETI research today. Medieval Islamic scholars like Al-Qazwini wrote detailed treatises on the possibility of inhabited worlds, describing civilizations that might exist on the moon and planets. In 13th century Europe, Thomas Aquinas seriously considered whether angels might inhabit the celestial spheres, essentially proposing that space itself might be filled with intelligent beings operating according to physical laws we didn't yet understand. But it was Giordano Bruno in the late 16th century who most clearly articulated the vision that would eventually lead to modern SETI. Bruno proposed that the stars were distant suns, each potentially surrounded by inhabited worlds. He imagined a universe teeming with life and intelligence, connected by invisible threads of communication and mutual awareness. The Catholic Church burned him at the stake in 1600, partly for these heretical ideas about cosmic plurality. The invention of the telescope in the early 17th century seemed to confirm Bruno's vision. Galileo's observations of the moons of Jupiter showed that other worlds did indeed exist, and they followed the same physical laws that governed Earth. If Jupiter had moons and those moons had surfaces and possibly atmospheres, why couldn't they have life? The question became not whether other inhabited worlds existed, but how we might detect them. By the 19th century, serious scientists were proposing methods for communicating with extraterrestrial civilizations. Carl Friedrich Gauss suggested cutting vast geometric patterns into the Siberian forest, figures large enough to be visible from space and complex enough to demonstrate terrestrial intelligence. Others proposed using mirrors to flash sunlight toward Mars during its closest approach to Earth, or burning enormous fires in the Sahara Desert arranged in mathematical patterns. The real breakthrough came with Heinrich Hertz's demonstration of radio waves in the 1880s. For the first time, humans had discovered a form of communication that could travel through the vacuum of space at the speed of light, potentially allowing near-instantaneous contact across interplanetary distances. Nikola Tesla, working in his Colorado Springs laboratory in 1899, became convinced that he was receiving radio signals from Mars, structured patterns in atmospheric noise that seemed too regular to be natural phenomena. Tesla was almost certainly wrong about the source of those signals, but he was right about the principle. Radio waves offered the first realistic possibility of detecting communications from other worlds, or at least recognizing technological signatures that would indicate the presence of advanced civilizations. By the early 20th century, scientists were seriously discussing the technical requirements for interstellar radio communication and the kinds of signals we might expect to receive. This historical context helps explain why SETI feels both revolutionary and inevitable. We're not imposing modern technological concepts on an ancient question. We're using modern technology to pursue one of humanity's oldest and most persistent curiosities. The radio telescopes and signal processing computers are just the latest tools in a search that has been going on for as long as humans have looked up at the night sky and wondered if anyone was looking back. When SETI researchers detect an ambiguous signal, they're not just processing electromagnetic data, they're participating in a conversation that stretches back thousands of years, adding their voices to a chorus of human voices that have always wondered about our cosmic companions. The universe is constantly broadcasting, filling space with electromagnetic signals that range from the whisper-quiet hydrogen line at 21 centimeters to the thunderous radio roars of distant quasars. Most of this cosmic chatter follows patterns we've learned to recognize: the predictable pulses of pulsars, the broad-spectrum static of thermal radiation, the characteristic signatures of stellar formation and galactic collisions. But embedded within this natural symphony are signals that don't quite fit, patterns that make experienced radio astronomers pause and take a closer look. The most famous of these cosmic anomalies remains the WOW signal detected by Jerry Amon at Ohio State University's Big Ear Radio Telescope on August 15, 1977. The signal appeared in the constellation Sagittarius, peaked at exactly the frequency that hydrogen atoms emit when they flip their electron spin, a frequency that many SETI researchers consider the most logical choice for interstellar communication because any technological civilization would know about it. The signal was strong, about 30 times more intense than the background noise, and it showed the characteristic pattern of a source moving across the sky as Earth rotated. What made the WOW signal so compelling wasn't just its strength or frequency, but its duration and behavior. It lasted exactly 72 seconds, which matched perfectly with the time it would take for a stationary source to pass through the telescope's beam as Earth turned. If the signal had been caused by terrestrial interference, it would have lasted longer or shown different timing patterns. If it had been a malfunction in the telescope itself, it would have appeared in both of the instrument's detection channels, but it only showed up in one. Despite numerous follow-up observations using more sensitive equipment, the signal has never been detected again. Its source region has been monitored extensively by radio telescopes around the world, but the cosmic coordinates that produce that tantalizing 72-second whisper have remained silent for over 40 years. But the WOW signal is just one entry in a growing catalogue of anomalous detections. In 1986, scientists at the Medicina Radio Observatory in Italy detected a signal they called SHGB02+14, which appeared intermittently over several years before fading away. Like the WOW signal, it was narrow-band and came from a specific location in space, but it defied easy explanation and eventually disappeared from the observational record. More recently, the Breakthrough Listen project, funded by entrepreneur Yuri Milner and utilizing some of the world's most sensitive radio telescopes, has detected a handful of signals that resist conventional explanation. BLC1, discovered in 2019 during observations of Proxima Centauri, appeared as a narrow-band signal at around 982 MHz, drifting slowly in frequency in a way that suggested it was coming from a source moving relative to Earth. The signal appeared multiple times over several months before disappearing, and its characteristics didn't match any known natural phenomenon or human-made interference. Initial excitement about BLC1 was tempered when researchers realized that similar signals could potentially be generated by malfunctioning electronics on Earth, but the case remains intriguing because of the signal's apparent association with Proxima Centauri, the nearest star to our solar system and the host of at least 2 confirmed exoplanets. These headline-grabbing detections represent just the tip of a much larger iceberg. SETI researchers regularly encounter signals that are interesting enough to warrant follow-up observations, but not quite compelling enough to claim as evidence of extraterrestrial intelligence. The Berkeley SETI Research Center maintains a database of candidate signals that includes hundreds of detections over the past several decades: radio bursts, structured patterns in cosmic noise, narrowband transmissions that appear briefly and then vanish. Most of these signals eventually receive mundane explanations. Satellites drift through the telescope beam, generating brief but intense radio bursts. Military radar installations bounce signals off the moon or atmospheric layers, creating phantom sources that appear to come from deep space. Solar flares and other stellar events can generate radio emissions that mimic artificial signals when seen through the filters of automated detection systems. But the process of elimination leaves a residue of genuinely puzzling detections, signals that don't match any known natural phenomenon but fall short of the extraordinary evidence that would be required to claim contact with extraterrestrial intelligence. They exist in a liminal space between the mundane and the revolutionary, cosmic murmurs that suggest the universe might be more active and interconnected than our models predict. What makes these cosmic signals so unsettling is how they seem to hover right at the edge of meaning, like fragments of a conversation overheard in a crowded room, where you can't quite make out the words but sense that something important is being discussed. The technical details of these detections reveal patterns that are difficult to explain using conventional astrophysics, yet they stop just short of the clear, unambiguous signatures that would constitute proof of extraterrestrial intelligence. Consider the timing characteristics of many candidate signals. Natural radio sources in space tend to follow predictable patterns. Pulsars spin with clockwork precision, variable stars brighten and dim according to well-understood physical processes, and even chaotic events like stellar flares or galactic collisions produce radio emissions that match theoretical models. But some of the signals detected by SETI searches show timing patterns that are more complex, more structured, almost as if they're carrying information encoded in their temporal variations. The WOW signal's 72-second duration is a perfect example. That's an oddly specific time frame, long enough to rule out most forms of terrestrial interference, but short enough to suggest that whatever produced it was operating according to some kind of schedule or protocol, rather than the random fluctuations we associate with natural phenomena. It's worth thinking about what kinds of natural processes could produce such precisely timed radio bursts, and the list of plausible candidates is surprisingly short. Then there's the frequency selection. Many of the most intriguing SETI detections occur at specific radio frequencies that have special significance for technological civilizations. The hydrogen line at 1420 MHz is a favorite because it's produced by the most abundant element in the universe. Any civilization capable of radio astronomy would necessarily discover this frequency, but some signals appear at harmonics of the hydrogen line, or at frequencies related to other fundamental physical constants, suggesting that whatever is producing them might be choosing these frequencies deliberately. The BLC-1 signal from Proxima Centauri showed another puzzling characteristic: frequency drift. Over the course of several hours, the signal's frequency shifted slightly, but consistently, behavior that's consistent with a source that's moving relative to Earth. This could indicate a natural explanation, like a rotating asteroid with unusual radio-emitting properties, but it could also suggest a signal originating from the surface of a planet orbiting Proxima Centauri, where the rotation of the planet would cause exactly this kind of frequency drift. Even more intriguing are the signals that show apparent modulation, variations in intensity or frequency that suggest they might be carrying encoded information. Several candidate detections over the past 2 decades have exhibited patterns that resemble the kind of digital modulation schemes used in human communications technology. These signals show rapid variations in amplitude or phase that are difficult to explain through natural processes, but would be exactly what you'd expect if someone was using radio waves to transmit data. The challenge is that all of these characteristics could potentially have conventional explanations. Pulsars can exhibit complex timing variations due to interactions with binary companions or changes in their magnetic fields. Interstellar scintillation, the twinkling effect caused by density variations in the space between stars, can cause apparent frequency drift and modulation in signals from distant sources. Solar wind interactions with planetary magnetospheres can generate structured radio emissions that mimic artificial signals, but the statistical clustering of these anomalous characteristics is what makes the signals so compelling. It's one thing for a natural source to occasionally produce a signal with one unusual property. It's quite another for multiple independent detections to show combinations of characteristics that are individually explainable but collectively improbable. There's also the geographical clustering to consider. Some regions of the sky seem to produce more candidate signals than others, particularly areas that are rich in nearby star systems known to host exoplanets. The Vega system, Tau Ceti, and the Alpha Centauri complex have all been associated with multiple anomalous detections over the years. This could be selection bias. We tend to point our most sensitive equipment toward nearby stars that might harbor life. But it could also suggest that whatever is producing these signals is more common in stellar neighborhoods that are conducive to the development of technological civilizations. Perhaps most puzzling of all is the apparent coordinated nature of some detections. On rare occasions, multiple radio telescopes separated by thousands of miles have detected similar signals from the same sky coordinates within short time periods, ruling out local interference but raising questions about what kinds of cosmic phenomena could produce such precisely synchronized radio emissions. When faced with signals that resist conventional explanation, researchers inevitably begin to explore more speculative possibilities, theories that push the boundaries of what we normally consider within the realm of scientific inquiry. The cosmic murmurs detected by SETI searches have prompted exactly this kind of creative thinking, leading to hypotheses that range from exotic astrophysics to considerations about the nature of intelligence itself. The most straightforward interpretation is that some of these signals represent genuine attempts at communication by extraterrestrial civilizations. This doesn't necessarily mean deliberate messages directed at Earth. They could be leakage from powerful communication systems, the electromagnetic equivalent of city lights visible from space, a civilization using radio waves for their own purposes, navigation beacons, power transmission, or communication between planets in their system might inadvertently create signals strong enough to be detected across interstellar distances. This leakage hypothesis is particularly intriguing because it suggests we might be detecting civilizations that aren't even trying to communicate with us. Their radio signatures would be byproducts of their technology rather than intentional signals, which might explain why the signals appear structured enough to be artificial but not obviously designed for interstellar communication. A navigation system broadcasting precise timing signals throughout a star system, for instance, might produce exactly the kind of narrow-band, periodically modulated transmissions that SETI searches occasionally detect. More deliberately, some researchers have proposed that advanced civilizations might use specific frequencies and modulation schemes as a kind of universal calling card, signals designed to be recognizable to any technological species capable of radio astronomy. The use of the hydrogen line frequency in several candidate detections fits this pattern. It's the cosmic equivalent of placing a message in a bottle where you know someone will eventually look. But the communication hypothesis raises its own puzzles. If extraterrestrial civilizations are trying to communicate, why are their signals so brief and sporadic? Why don't they repeat their transmissions or use more obviously artificial patterns? One possibility is that we're detecting civilizations that are much more advanced than our own, using communication technologies that are barely comprehensible to us. Their signals might be incredibly information-dense, packing vast amounts of data into brief transmissions that appear as simple radio bursts to our relatively primitive detection equipment. Another theoretical framework involves the concept of directed panspermia, the idea that life on Earth might have been seeded deliberately by an extraterrestrial intelligence billions of years ago. If this were true, the cosmic murmurs could represent check-in signals from our cosmic benefactors, periodic transmissions designed to monitor the development of intelligence on worlds they've seeded with life. This would explain why some signals seem to appear at moments of technological transition in human history, and why they often seem just barely detectable rather than overwhelming obvious. More speculatively, some researchers have connected the anomalous signals to theories about the nature of consciousness itself. If consciousness is a fundamental property of the universe rather than an emergent property of complex matter, then sufficiently advanced forms of awareness might be able to manipulate electromagnetic fields directly, creating radio signals through mental processes rather than technological ones. This consciousness-based communication model would explain why the signals often appear to have information content, but don't follow the engineering patterns we'd expect from conventional radio technology. There's also the possibility that we're detecting evidence of civilizations that exist on completely different timescales than our own. A species with lifespans measured in thousands or millions of years might communicate using signals that repeat over similarly extended periods. What appears to us as a brief, non-repeating signal might actually be part of a conversation that spans centuries, with response times that dwarf human attention spans. The simulation hypothesis offers yet another lens through which to view these cosmic murmurs. If our reality is some kind of computational process, the anomalous signals might represent communication between different instances of the simulation or messages from administrators of the system. They might be the equivalent of system notifications or debugging information, signals that leak through from the computational infrastructure that generates our experienced reality. Perhaps most intriguingly, some theorists have proposed that the signals represent evidence of intelligence that operates on galactic scales, cosmic minds that use stellar engineering and gravitational manipulation to communicate across vast distances. From this perspective, what we interpret as radio signals might be the electromagnetic shadows of engineering projects so vast that we can only detect their side effects, like ants observing the radio emissions from a city and trying to understand the civilization that created them. These theories force us to expand our conception of what intelligence might look like when it operates on cosmic scales and timelines that dwarf human experience. Before we venture too far into exotic theories about galactic civilizations and cosmic consciousness, it's worth considering the more conventional explanations that could account for these puzzling signals. The history of science is filled with mysterious phenomena that eventually yielded to more mundane explanations, and the principle of scientific skepticism suggests we should thoroughly explore prosaic possibilities before embracing more speculative alternatives. The most obvious explanation for many candidate signals is terrestrial interference masquerading as extraterrestrial communication. Despite the best efforts of SETI researchers to filter out human-made signals, our planet is awash in electromagnetic radiation from countless sources: satellites, radar installations, communication networks, and industrial equipment. These signals can bounce off atmospheric layers, reflect from nearby aircraft, or scatter from terrestrial objects in ways that make them appear to originate from deep space. Modern life has made this problem exponentially more complex. The proliferation of cell phone networks, GPS satellites, and wireless communication systems has created an electromagnetic environment that's orders of magnitude more complex than what existed when SETI searches began in the 1960s. A signal that appears to come from the direction of a nearby star might actually be leakage from a communication satellite, whose position in space creates the illusion of an extraterrestrial source. Radio frequency interference isn't limited to deliberate communication systems. Solar panels, computer processors, and even LED light bulbs can generate electromagnetic emissions that, under the right conditions, might appear as structured signals from space. The challenge for SETI researchers is that these interference sources are becoming increasingly sophisticated and harder to distinguish from the kinds of signals they're actually hoping to detect. There's also the question of observational bias and pattern recognition. Human beings are extraordinarily good at finding patterns in random data. It's one of our species' most valuable survival traits, but it can lead us astray when we're analyzing complex data sets. When you're looking at millions of radio measurements collected over months or years, statistical fluctuations will inevitably produce apparent patterns that seem meaningful but are actually just random noise. This is particularly problematic in SETI research because the signals being sought are, by definition, rare and unusual. Researchers are specifically looking for anomalies, which means they're inherently more likely to catalog interesting coincidences as potential detections. The human tendency to see faces in clouds or hear voices in static can easily extend to seeing artificial patterns in cosmic radio emissions. Natural astrophysical phenomena can also produce signals that mimic artificial transmissions under certain circumstances. Rotating neutron stars with irregular magnetic fields can generate radio emissions that appear structured and artificial when filtered through automated detection systems. Interstellar scintillation can cause natural radio sources to appear to flicker or modulate in ways that resemble data transmission. Even something as prosaic as solar wind interactions with planetary magnetospheres can create radio signatures that appear anomalous to observers unfamiliar with the relevant physics. The discovery of fast radio bursts in the past 2 decades has revealed an entire class of cosmic phenomena that produces brief, intense radio signals of exactly the type that SETI searches are designed to detect. These bursts appear to originate from distant galaxies and are almost certainly natural phenomena, but they demonstrate that the universe is capable of generating radio signals that are far more exotic and structured than astronomers previously imagined. Pulsar glitches represent another natural phenomenon that can produce apparent anomalies in radio observations. When the crust of a neutron star suddenly shifts, it can cause dramatic changes in the star's rotation rate and magnetic field configuration, leading to radio emissions that are completely unlike the star's normal behavior. These events are rare and unpredictable, which means they can easily be mistaken for artificial signals by automated detection systems. Perhaps most importantly, there's the challenge of confirmation and repeatability. Science works by requiring that extraordinary claims be supported by extraordinary evidence, and that significant discoveries be reproducible by independent observers. The vast majority of candidate SETI signals fail this test. They appear once and then vanish, leaving researchers with tantalizing hints but no way to verify their findings or rule out mundane explanations. This doesn't mean that all anomalous signals can be dismissed as observational errors or natural phenomena, but it does suggest that we should approach each detection with appropriate scientific skepticism. The universe is under no obligation to make sense to us, and our current understanding of astrophysics is certainly incomplete. But the history of science strongly suggests that exotic explanations should be the last resort rather than the first assumption. So here we are, decades into humanity's systematic search for cosmic companions, with a collection of tantalizing signals that whisper possibilities but refuse to speak clearly. The cosmic murmurs we've explored tonight exist in that uncomfortable space between the known and the unknowable, between the mundane and the miraculous. They remind us that the universe still holds secrets capable of making us pause, wonder, and question our assumptions about our place in the cosmic order. What strikes me most about these ambiguous detections is how they mirror the fundamental loneliness and hope that drives human curiosity about the cosmos. We built our radio telescopes and trained them on the stars, not because we were certain we'd find someone listening, but because the possibility of cosmic solitude was too terrible to accept without at least trying to prove it wrong. Every candidate signal, no matter how brief or ambiguous, represents a moment when that cosmic loneliness might have been broken. But maybe the signals themselves are less important than what the search reveals about who we are as a species. The fact that we've spent enormous resources and decades of effort listening for voices in the cosmic static says something profound about human nature. We're a species that can contemplate infinity, that can imagine minds vastly different from our own, that can build machines capable of detecting whispers from across the galaxy. Whether or not anyone is whispering back, the search itself is a remarkable achievement. The ambiguity of these cosmic murmurs might actually be their most significant feature. Clear, unambiguous contact with an extraterrestrial civilization would certainly transform human civilization, but it would also answer the question definitively and bring the search to an end. The uncertain signals keep the question alive, keep us wondering, keep us reaching toward something beyond ourselves. There's something beautifully human about our response to these ambiguous signals. We don't simply catalogue them and move on. We theorize, we speculate, we imagine what they might mean and where they might come from. We populate the cosmos with our hopes and fears, projecting consciousness and intention onto electromagnetic patterns that might be nothing more than cosmic noise. In doing so, we reveal as much about ourselves as we do about the universe we're exploring. The search for extraterrestrial intelligence forces us to confront fundamental questions about the nature of intelligence itself. What would minds that evolved under different stars think about? How would they perceive reality? What would they consider worth communicating across the vast emptiness between worlds? These questions don't have answers, but thinking about them expands our understanding of what consciousness might be capable of when it's not constrained by terrestrial biology and human cultural assumptions. Whether the cosmic murmurs represent genuine attempts at communication, exotic astrophysical phenomena we don't yet understand, or simply the inevitable result of looking for patterns in vast amounts of data, they've already accomplished something important. They've kept alive the possibility that intelligence and curiosity are not unique to Earth, that somewhere among the billions of stars in our galaxy, other minds might be contemplating the same questions that drive our own cosmic investigations. The radio telescopes will keep listening, the signal processing algorithms will keep running, and the cosmic static will keep whispering its ambiguous secrets. Some of those whispers might eventually resolve into clear messages from our cosmic neighbors. Others will fade into the background noise of an indifferent universe. But the search itself will continue, driven by that uniquely human combination of curiosity and hope that refuses to accept cosmic solitude as the final answer. In the end, perhaps the most profound discovery isn't waiting somewhere out there among the stars. Perhaps it's the recognition that a universe capable of producing minds curious enough to listen for each other is already more extraordinary than we have any right to expect. The cosmos is murmuring, we're listening, and in that simple act of attention, something remarkable is happening regardless of what we ultimately hear in response.